All right, today we're gonna do our first water jet, and we're also gonna do our first elbow questions today on this little YouTube video. All right, so our first example today is 6.8 in our textbook, and the Hibbeler fluid mechanics, and we are given V initial, which is the initial velocity of the nozzle that's shooting at the wall, and it kind of looks like this. It's like it's really like this, like a water just shoots at this 45-degree wall, and it just pushes that other water, which would be V2, at a slanted 45-degree angle back towards the nozzle, which was originally shooting at that curved wall. So it's just gonna be like this. VI is the pen. Boom, angle, out. So one of the equations we get for these type of scenarios would be like summation, because all the forces, Vx equals M out, or actually let me find the equation. Yeah, it is that minus M in, I believe. Whoops, it's not in. It's not in. It's not in. It's Fx equals M 2x minus M 1x. And then you would have to break it up into M 2y minus M 1y, and then to solve for the total resultant force. If you remember from statics, we have x squared plus fy. Get away from my screen. Fy squared. So we are given our initial velocity, which is 20 meters per second, and we are trying to find our what are we trying to find? We are trying to find our force in the x direction. So they only want our horizontal force, which would be this side, because horizontal, side to side. So we're just looking for our fx force in this scenario. But I will solve for both in another example. So the first step to this equation will be to solve for our m dot. And our m dot would be equal to actually, something's wrong with this formula. I'm trying to figure out what. Let me flip through the notes real quick. Oh, whoops. Okay, my fault, guys. My fault. This is the formula. Fx equals m v2 minus v1. Yeah, I was wondering why it was looking weird. Yeah, this is the formula. My fault. And both these velocities are also based in the y, and this is based in the x, and that's very important, or you're gonna mess up the whole equation and you're just gonna get a completely wrong answer. So the first thing you're gonna do is you're gonna solve for m dot. The m dot's gonna be the same because remember, conservation of mass. So that's gonna be the same. That's why these are still there. But the velocities are gonna be different. So m dot equals pq, and we don't have q, but we do have our velocity and area, if you can see in the 40 meters which is a hint that we can solve for area. And in this case, this is water, and we are doing a SI, so it will be 1,000 times pi 20 times 10 to the negative 3, respect the negative, respect the units, times velocity, which is 20, and that would equal where's my calculator? That would equal 1,000 that would equal 25 kg per second. All right. So since our equation is V2 minus Vx, you also have to respect the direction, because the direction matters in these scenarios. Because I'll just explain it. I'll show you. So we're looking for our x, and by the way, nozzles don't have a force, so the only force is going to be the normal force of the wall right here. Because every single time in these equations, these water jets hit a wall, you're going to have a normal force to account for, which would only be Fx, actually, because there's not going to be a Fy, because it only hits a horizontal. So we're solving for that Fx, and you notice the normal force is going to, like, if the water is hitting this way, it's going to go this opposite direction. It's going to meet that force and bounce off of each other. So this force is going to crash into here, and it's just going to bounce off. So I'll be right back setting up the equation. So here is how it's set up right here, and don't mind the cut on my fingers. I just cut myself with a knife earlier. So these type of problems, these water jet problems, really emphasize the importance of directions and magnitudes of both velocities. So if one velocity is going in the positive direction, which is the normal x positive, this one's gonna bounce off. So you're gonna have to subtract the V2 because it's going to the negative direction, because you have to add that negative, because it's V2 minus V1. So it's really, in this scenario, it's gonna be minus, and it's gonna become a bigger number. So you're gonna see that Fx is gonna be a big negative number. And you know you're gonna be doing these scenarios, right? When you're automatically, it's just gonna figure itself out. So solving for this, you're gonna see that 853.5 newtons is your answer. But you know that this is actually right, and you do the directions right. When you get that, then the negatives cancel out and you get a positive answer. Just a way to check yourself. That was a super quick burst problem, but here's your steps. Step 1, account for initial velocity and direction. And just use the typical, coordinate system, y plus, x plus. Step 2, you know that when you have a water bashing against the wall, it's gonna have a normal force, and I'm just gonna put F normal. So you're gonna have to account that as your force for this scenario, because every single type of these problems is gonna hit some sort of like wall. So it's gonna bounce off and have a normal force. Depending if that wall is at an angle or not, that depends on the problem. But it's always gonna have a normal force on that surface, which is perpendicular to the surface. So this is gonna bash here. And also, most importantly, account for directions. I'm gonna do more of one video for this, because this is just super quick and just a simple rundown, but this is part 1 of it.